There's a property of resistors that is often overlooked. They generate noise. Every resistor does, regardless of type or quality. This is a fundamental phenomenon known as thermal noise, or Johnson-Nyquist noise. It arises from the thermal motion of charge carriers and exists in any conductor at any temperature above absolute zero. It cannot be eliminated, only accounted for and minimized. Quantitatively, this noise is straightforward. The noise voltage density is proportional to resistance and temperature. For example, a 1 kΩ resistor at room temperature produces approximately 4 nV Hertz. Now let's calculate further. If the signal bandwidth is 20 kHz, the total noise is 4 nV 2000. This gives roughly 0.5–0.6 UV. For certain types of circuits, that is already a significant noise level. Such noise is unacceptable in applications dealing with very low-level signals, strain gauges, current shunt measurements, thermocouples. In sensitive analog front-ends, this noise directly impacts measurement accuracy. That is why in equivalent circuit models, a resistor is represented not only as a resistance, but also as a noise voltage source. From there, everything depends on the application. If it's a current-limiting resistor for an LED, the noise is irrelevant. But if it's a high-value resistor, say 1 mho in the feedback network of an operational amplifier, its intrinsic noise can become dominant, and that noise will then be amplified by the entire signal chain. This leads to a somewhat counterintuitive situation. The amplifier is low noise, but the resistor is not. Therefore, in the design of precision and measurement circuits, resistor noise is not a secondary effect. It is a primary design parameter. Everything matters: resistance value, bandwidth, and resistor technology. If you found this video helpful, give it a like, subscribe, and check out the channel. We've got plenty of useful content on electronics.